Alrighty, so now that we have a full data set collected, I'm going to open up Apex3, enter in the login, just default as guest. So if you're transferring your frames to a different computer, like a faster one like I did in this case, you just create a new name, and I just renamed it the same thing, and then you're just going to dump the frames into that folder that you just created. So, and it would be empty, but all you really need is those frames and possibly the VZS file for the video of the crystal. But I already did that, so enter in the basic information again if you did do that. We're going to go to determine unit cell, and we're going to harvest the spots. I already did that here. And you're going to enter the number of runs there were for the data collection that you did, and you can enter images per run. I just increased this to 30. The number of runs is that first digit, so in this case it's 36 runs, and then there's a number of frames per run. I just keep the minimum intensity per sigma the same, and then you can either index this now, or you can take a look at the reciprocal lattice after you've harvested the spots. I like to do that sometimes. There's a couple of reasons to do this. One being if you know the crystal is twinned, or there are inclusions of other crystals in it, or there's something messed up about the crystal, you could pick out the intensity maxima that correspond to the main lattice you're interested in. You could separate them out even. There's a lot of applications to this, but it's a good practice probably to just solve it normally at first, and then do this hand picking. I decided to just go ahead and hand pick some of these bad reflections, or these reflections that don't correspond to the main lattice, that stick out to me. But this is totally optional. But yeah, in this case it's very easy to see that there is what is a part of the main lattice and what is apparently not. These two reflections, for example, definitely not. And then I just move them to one of the groups. In this case it's just the red group, and then I do all of my data reduction and everything on the gray group. But yeah, as I said, this is the best application for this is for twinned crystals. It's probably the best way of dealing with twinned crystals, honestly. And anytime you have multiple crystals in the same thing, in the same scan. And once you're done with that, you can delete these if you want, delete the non-visible, and then I'll just continue to the unit cell determination from the full data set. So I'm going to use that gray group and index it. And with this particular crystal, this is probably the hardest part, which sounds weird, but this crystal has a very unusual structure in that it's almost face-centered orthorhombic, which means that there can be multiple C lattices centered to it, and some of them that are erroneous monoclinic C lattices. So that's why I picked this as an example to work with the EXCELIBR spreadsheet. And I find that this lattice indexing doesn't always find the correct lattice, or the one that I'm looking for, at least to put this in the conventional setting, which is what, if you're going to publish a structure, you need to do in mineralogy at least. So now I'm just going to click refine once, and it selected over 1,000 reflections for refinement. I'm going to just accept that for now and go to the Bravai lattice. So you could see that ordinarily you would pick orthorhombic face-centered for this because it gives it a really good score for the field of merit. But if we go to refine, at some point you would figure out that this wasn't correct, but here's one way of figuring it out. So I click refine and it looks good. Everything fits great. But when you go to transformations, here's the orientation matrix for this lattice. And I already collected the orientation from the optical data. So we're going to go to that to my spreadsheet here. So down here there's the XRD orientation matrix, which is in reciprocal space. That is the same world as what you saw listed on Apex3. So if you entered that and tried to relate it to the setting that I determined from the spindle stage, you can compare those two lattices. So here I'm going to enter that. It's already filled in with something I tried before, but I'm just going to go through that. So we're going to enter this orientation matrix in here. And this is way more work than you normally would have to do with a crystal. It just so happens that this one is very problematic for finding the crystallographic setting to use. Alright, and that's our plot. So what we see is that C is equal to Z, but A and B don't correspond to X and Y. So if the optical vectors don't correspond to the crystallographic vectors, the principal optical vectors, then it cannot be orthorhombic. That makes no sense. So we know that it has to be monoclinic of some kind, because one of the crystallographic axes does correspond. I mean, it could be triclinic, but it's unlikely in this case, but most likely it's monoclinic, especially with that really high field merit. But now we have to find the correct monoclinic setting, because this has to be monoclinic C. Because there's no such, I mean there is such thing as monoclinic F settings, but that's a non-conventional setting. So we have to find the correct C lattice setting, and that is quite a chore in this case. But at the very least, what I could tell is that there's probably a setting that's very close to that orthorhombic one that we could use, where that C axis was equal to Z. I'm almost certain that that has to be B, the twofold axis. So Z is probably equal to B, which is also what's suggested in the spreadsheet from our work from earlier. And B is over here by Y. Yeah, so this setting doesn't work at all either. So the one that so what's wrong with this one is it looks great on the XRD, on the X-ray information here. But for whatever reason, the lattice that this picked, none of the crystallographic vectors correspond with the optical vectors. And we're quite sure that it's supposed to be monoclinic. So that means that it can't be the setting either. If A, B, and C none of those correspond with X, Y, or Z, no way that is monoclinic. It could be triclinic, but a more likely explanation is that we're just not finding that C lattice setting, and we're going to have to enter it in manually or rely on this least squares method to find that setting. But this ends up taking forever. I've done this lattice before, and it found it, and it was only the least squares fit that worked to find the correct setting, but it just gets hung up here, so I'm just going to fast forward through this, and I'm going to enter a orientation matrix manually, using information from the internet about scolecite and information I figured out from the optical crystallography we did using the spreadsheet. So we pretty much determined that Z is B, and the long axis of the crystal is either A or C. So that just leaves one other axis to find, really. And because the beta angle is 108 or 109 or so for the conventional C lattice setting for scolecite, we can just use a rotation matrix to try to find that axis. And this one is really specifically unusual in that way because there are two axes that will work for the C axis in this case. So the long axis of the crystal for this is actually A. B is equal to Z in the correct setting. And the C axis can either be 108 degrees away from A and normal to B in one direction or the other. It just so happens that 108 degrees either way has very similar translational characteristics for scolecite. So you can get mixed up with that too, and I've had that happen on here with this example. So it's really confusing, but ultimately I figured it out, and the beta angle that I have to enter here is around 71 degrees because it will only rotate clockwise, and that's the axis that works for the conventional setting for scolecite in monoclinic C. So here, yep, C is equal to Z, which means C is actually B. And that A is truly A, actually. But the B axis here, which is supposed to actually be C, is not 90 degrees away, actually. So we have to figure that part out. I created a spreadsheet to where you can use the microscope orientation for A, B, and C as a reciprocal lattice setting. So this is in direct space, but we can just convert that to reciprocal space and scale it by the correct cell parameters to try to find the right reciprocal lattice. Yeah, as you can see, that A is equal to C in this, and then A of the XRD orientation is equal to, or B of the XRD orientation is the same as A of the microscope orientation. What you can do is go to the American Mineralogist Crystal Structure database, enter in a mineral, and see if someone is published in that particular lattice. So this one is solved in CC for those lattice parameters. There are old settings listed below this publication in the F1D1 lattice, which corresponds to that orthorhombic face-centered lattice, but of course it's actually monoclinic and it's non-standard. And to do that, I just enter the lattice parameters to scale the matrix correctly, and hopefully you have the right microscope orientation matrix. And that could be some trial and error, but in all likelihood you won't have to do all this with a normal crystal. I just picked this one because it's the hardest, it's the most difficult possible scenario with centering a correct lattice for a mineral. Alright, so this is the correct spreadsheet to use. I found the A-axis, which was the long axis of the crystal in this example. Entered my beta angle, and I have my microscope orientation matrix. So if I want to use the microscope orientation matrix, I need to go down here. And notice that this is about 110-degree beta angle. There's something unusual about the setting that was chosen for this publication as well. And we'll run into that later. But, you know, just to keep things consistent, we're going to use their setting. Okay, so B is equal to Z. That's correct. That's good. A is right. And C, that's actually the C axis that I want in this case. If I use 109, it'd be out there. It just so happens, like I explained, it just so happens that that axis has similar translational characteristics as the alternative one, even though they are different directions. But this is the correct setting to use. This plot will only project upper hemisphere axis, or it'll only plot upper hemisphere axes. Beta here between A and C would be acute because it's performing the rotation clockwise, but technically the C axis would be in the lower hemisphere, so that A was positive A, B was positive B, and C was positive C. Going back to this monoclinic setting so that at least it will try to find a monoclinic C setting. Click Refine. Refine that a little bit. And now I'm going to manually enter this orientation matrix, which I actually just need to paste the values. Yep. And since that uses an acute beta in this matrix, we're going to just change that. All you need to do is make A star and B star negative, or opposite sign for each component of each vector. That has the right lattice parameters. Let's just hope. Okay, it looks bad right now, but we'll click Refine and see if it finds those spots. And it does, which is just great. So finally, we have the correct starting point at least. Like I said, normally you wouldn't have to do any of that. Just find a lattice and then proceed to the next part. And if we look at our reciprocal lattice, there are our reciprocal lattice vectors, which look good. We can orient this and look down each axis. That looks right. And since it's monoclinic, of course, reciprocal lattice vectors are going to be a little bit confusing. And then I have to re-index these because it was done in a different lattice setting. So I'm just going to clear this and redo this. Index each one of these planes that are, the dashed line is the normal vector to the plane. So just use that on both sides just to get a good crystal dimensions. And this crystal is kind of huge for doing X-ray diffraction on, but it's fine. It's not a very strong absorber. Normally you'd want something that's a little bit more equant and probably something about half this size if you just cut this across its length. But I like using this because it's easy for me to optically find where possible crystallographic axes are. Replace that face and go to describe samples, and we have our new dimensions. And yeah, this is a pretty long crystal. It's 700 microns. So yeah, between 100 and 200 is kind of what you want normally. And then we can integrate. We can integrate this lattice to optimize the translational vectors and model the intensity maxima. Start integration. And I'm doing this on a faster computer than the one that runs the instrument itself, but it still may take some time to integrate. There it goes, and sometimes the graphics card or something won't be good enough to display these or boxes in real time, but here we got a correlation coefficient in the upper left. You got the spot that it's modeling in the bottom left. In the upper right, I usually just close this one and open up the integration progress. Pixel error down below. So this is going pretty well because we have really high, good correlation coefficients for each of these. So we know that it found probably at least a usable crystallographic lattice. If it didn't, then these statistics would be really low and very high error. And that's done. And it kind of freezes up. But we can expand this window and look at our optimized orientation matrix. We can enter that in to our orientation matrix on the spreadsheet if you're still wanting to deal with this. Just so that you have a good plot of where the optical vectors are and the crystallographic vectors are. Alright, so this will just recalculate all those dimensions that are already listed, and it will plot, well, it won't plot it, but it'll give you the residual angle between your converted X-ray orientation and your microscope orientation. And as you can see, I also have to enter in the beta angle, which is 109.976. C has a little bit more error than the others, but as you can see, very, very close. And that's after transferring the goniometer from one place to another. And remember, that's purely just from the microscope orientation, just visually looking at indexing faces and determining the optical vectors and everything. So, looks pretty good. And that's what we have for a residual angle between the X-ray method and the optical way of doing this. And hopefully that matrix works, or that setting works. So now you're going to scale the data, make sure these are all operating on the same world here. As monoclinic, the Lowry group should be 2 RM. Start. Just gonna enter this as a medium absorber, and then click refine. And this converges on a reasonable R. And the R internal statistics, that's our scale factor. Our R internals are pretty low, which is good. We have good consistency among symmetrically equivalent spots overall. So yeah, that's pretty much scaling. Now we're going to determine the space group, and here, because of all that business with the unit cell, we have to be kind of careful. Normally you can just click through this, just enter until it closes. But here, as you can see, option B, it wants as the crystallographic setting, and that would probably be normally what you would want. But I'm trying to use the convention that was used by another author, so I'm just going to retain the cell that we determined already and select F. And after I do that, you can pretty much just click through this prompt. There's a lot on statistics about like symmetrically equivalent spots, rejected thresholds, and all this stuff. But if you have a good data set, you should be pretty much fine. Good combined field of merit, you want that to be near 1 for the CC space group. Needs a formula, a tentative Z. This doesn't have to be exactly correct. We're going to prepare the ShellX files and the HKL file. And then we're done with XPrep. So that went pretty smoothly, which is no surprise if you have good data and everything. I'm just going to reopen up the HKL file, just looking at the date modified on this to make sure that it is the one that I just did. Open that up. This is the correct lattice that I want to use. I'm going to click solve. And it solved for pretty well in CC already to begin with. A 3.3% for the R1. That's very good. Especially for a zeolite at room temperature. So I'm just going to click refine, copy res to ins. And I'm going to check some of these bond distances in the list file just to make sure that they make sense. That's okay. Yeah, that's fine. Those warnings are nothing to worry about, really. But, okay, looking at the bond lengths up here, so we have Ca to oxygen, I, E, J, G. Those are all around 2.3, and then there's one that's 2.5. That's good. That makes sense. All the SIs are about 1.6 angstroms from oxygens, so that works for oxygens. The aluminum's 1.7. That all makes sense. So it really did find the correct atom assignments and everything in this example. Sometimes if you have magnesium or something in the structure, it'll mix up that with a calcium, and that is pretty obvious. MgO should be about 2 angstroms, CaO is about 2.3. And then here, since I'm pretty sure that I put this in the convention that they are using in this publication, these waters are just going to be oxygen atoms, and I'll attach some hydrogens later. Since I'm pretty sure that I got that figured out, I like to prepare these files, these templates, so that I can just paste them into the structure and not have to think. But I'll run through this example just to show a pretty basic refinement. I'm not an expert on refinement by any means, but I'm good enough to get this done. So I'll just minimize that and open up their structure over here. What you have to do, if you use the right lattice and you want to put this in convention, you have to paste these fractional coordinates into each atom. So just copy and paste, and if I did pick the right lattice that corresponds, then this should have no problems. If it has problems, then you probably picked the wrong lattice. So I'm just going to fast forward through this. And okay. Alright, that looks good. I dampened the structure. Damp 1000 is the command, just in case it blows up. That will control it a little bit. And this actually worked immediately because it's in the correct convention, or it was the correct lattice after all. So those are the fractional coordinates you want to use. And I will take away the damp command. Yeah, it's just a way of controlling how aggressive the refinement goes. And I'm going to paste the weighting scheme here. Click Refine. I'm going to put an extinction correction here. There's you can always put an extinction command in this. There's nothing wrong with having that in general. And I'm going to just rename these really quick just to make them more similar to their naming here. And then 1, 2, 3, 4. I'm going to rename these water molecules. I think this ShellX has a problem with names like that. So I'm just going to call them O1W, O2W. Now these are kind of high here, so, and that could just be because these, I'm not using thermal ellipsoids yet. And in the list file, this is a problem that you actually do want to worry about. Absolute structure cannot be determined. So our coordinates are fine, but it's suggesting that we invert the structure because there's something wrong with that convention, some symmetry element. So we're going to say move 1, 1, 1. Bar 1 to invert. And that drops the R down to 3.9%. That's good. And you see that now the convention is different. It's either supplementary coordinates or just shifted. I'm going to shift the weight and click Refine. And yeah, it's interesting to see this. It's sort of a supplementary fractional coordinates here. So yeah, for whatever reason, that setting with the crystal that I'm using here doesn't quite gel with these listed here. But I'm gonna copy res to ends and refine again. Copy res to ends, and that should clear it. There is those other warnings, but those are fine. It's just about the cell contents. Nothing changed. Now we want to go anisotropic, I'd say. So we're going to use anisotropic thermal ellipsoids because, you know, the temperature of the room, the atoms are going to have a little bit more displacement than in this model. So, and that will drop the R quite a bit. So now we're sitting at 1.8%. It's going to change the weighting scheme. Going to change that. And copy res to ends. Okay. Alrighty. So now I'd say, since there's not that much to deal with this structure, other than the hydrogens, it's about time to work on those. So some of these possible Q peaks here, or these Q peaks, are possibly hydrogen atoms, and it looks like I don't know, say the top 6 are candidates for being hydrogens in this example because of the electron density, or the difference electron density. And you can actually see them. That purple one there is Q2, and that sounds about right. It's about the right distance from the oxygens. In general, these tend to, the Q peaks are centered a little bit close to oxygens when they are, say, waters, but that's okay. And we can check the bond lengths from these Q peaks. So right here it says distance. That's a bit short for being a water molecule, but that's probably correct. So O1W, O2W, those have got to be hydrogens that go along with our water molecules. Alright, so we're going to go back to the instruction file. And I'm just going to copy these and paste these on. And I'm going to rename them H1 and so on. That number 1, if I haven't explained this yet, that number 1 goes with this structure factor because it's the number 1 element listed there. So that is hydrogen. For example, calcium is number 3 because it's the 3rd listed here. Si is 5. So that's how it actually knows which scattering factor to use, or just for your purposes what element to use. And the naming can be just whatever. Okay, so that dropped things a bit here. We're down to 1.67. But of course, some of these hydrogens don't make sense, like that one. But it's looking pretty good, and the hydrogens are behaving really well. In chemistry, you'll find that you have to put like all sorts of constraints on these to make them work, but to also make sense in your model. But these are behaving pretty well, even though the bond distances are probably wrong. But yeah, I think 4 and 5, yeah, those don't make sense. Those are not correct. There probably are 6 hydrogens, but these two are not the actual hydrogens. So I'm going to refine it without those two, since it's so stable. If it's not stable, you'll have to put restraints on those, and you can look that up on the ShellX commands list. Yeah, so now Q1 and Q2, those are probably the hydrogens we're looking for. So I'll just drag these up here, rename those 4 and 5. And since everything is so stable, I will just refine these without restraints or constraints. Okay, that's looking pretty darn good. But we have to make the bond lengths make some type of sense, because in water, the bond length should be about 0.96 angstroms, I believe. And that's what these seem to be. They're just water molecules that are surrounding those big calcium ions in this, or those big calciums in this very open structured zeolite. Yeah, see, like those bond lengths are way too close. That one's okay. That's a bit close. So I'm going to look up the ShellX commands. We're going to go to this website. And these are all the commands that you can use on ShellX. I think I've done this before and found that you have to use defix in this particular example. If you're using, like, if you're trying to model hydroxyls or something like that, you'd use hfix and whatever configuration it's in. But I'm just going to fix a bond length. Defix is just distance, fixing the distance per some standard deviation. And I'm just going to use the standard, or the default standard deviation. So all I have to list is defix, and then the bond length, which is 0.96, and then enter the atom that the hydrogen is bonded to and the hydrogen itself. But just to remember, yeah, so this is what I did before. I'm just going to copy this. Defix 0.96. It'll still probably be a little close to the oxygen, but that's okay. I'm fine with just using the regular standard deviation. And make sure, yeah, so these are hydrogens, so you don't want to use the anisotropy command for that either. It's just so low electron density. That's why it doesn't behave so well in these refinements. It has a very low scattering factor. Alright, use the proper names. And this is probably not going to make any difference in our R value, really. It's just to make sure that our model is correct. And it's impressive enough that we can even see these hydrogens with X-ray diffraction. Especially at room temperature where things are moving around. But I think this is a really good starting point for trying to perform structural refinements on a zeolite. Is something that's reasonably well structured, like scolecite. Water molecule bond length, yep, 0.96. And yeah, there's other things that you can do with ShellX. I don't really know how to do these, but I just know how to fix the angle or fix the distance. There are other ways of trying to fix angles and so forth, but yeah. So it went a little bit up, the R value, but that's fine. I'm perfectly okay with it because we know that our model is correct anyway. And from here, I'm just going to rename these just to clean things up, make sure it's oxygen 1W is H1 and 2, and alright, and I'll just shift our weight, click refine. Alright, looking pretty good. That's pretty much the basic structure at this point. To finalize the structure, you'll want to enter in an ACTA command to publish the structure as a CIF file, or to write the structure as a CIF file in that directory. The very last thing that you could do also is omit reflections, and I'll go through that in a bit here too. And I'm just going to, it's always a good idea to do this, is just a copy from lat on down to a text file so that you can always use that as a template or as a save. And ACTA, so this will write the CIF file. And then you can view the structure in whatever structure viewer you have. There are free ones like Vesta to plot it. And that's what our structure looks like. I don't know how to use Vesta very well. I'll try to do a polyhedral model. Yep, that did nothing. Okay. Alright. Oh, I probably needed to connect. Yeah, I probably needed to do another command. But anyway. There's our CIF file. And here's our list. Yeah, so the very last thing that you can do, make sure that you don't have any major problems here. Interesting. Okay. The most disagreeable reflections. So these disagree with our model due to maybe disorder or, periodic disorder. But we can just get rid of those, like if they are just from a little inclusion in the crystal or some defect in it. You can get rid of those reflections by using the omit command and entering in the HKL of those reflections. Just kind of paste them. And this will lower our R value just a little bit, but yeah, it doesn't matter too much. But it's just something you can do to finalize the structure. Then enter in your ACTA command. But if you omit a bunch of reflections, it really doesn't do anything, so there's not a whole lot of point in it. So I would just omit the top few that might be screwing with the model. But yeah, that's basically it.